is down there this time. Why is the camera below, and why is nobody responding to me? Good. Sandal, you were not in the lecture last time, if I am correct. Do you need to get access to that lecture? I can hear you. Great. Thank you, gentlemen. Let's make this small if possible. Yes, sir. Okay. Very good. Let's see. We have 7. Missing. I've got 1, 2 people missing. All right. I did manage to put the test 1 assignment on Blackboard. Here's my class roll. Is missing. Who else is missing? Kushner's there. Who's there? Cloud is missing, I think. All right. So what I'm going to do is go over it very quickly with you guys, so that if you have any questions, you can raise them. And let me share my screen. All right. Share the screen, share application screen, allow. Am I sharing? Yes, I am sharing. And it's again doing it. Multiple thingies. Give me a second. Alright, let's stop recording in case. Alright, let's see. Spring homework, we said homework, but I'll also put slash test. Alright. So this is test 1, which is now on Blackboard. Let me make this wide so that you can all read it. So this is the first project. This is in view of the first test, and I split it into 2 parts. First part to be finished a week from today, the 23rd, and the second part should be March 2nd, which I believe another 9 days or so. Okay, so the problem statement is very similar to the homework problem, last homework problem, except this time we are saying we are supposed to be designing the laminate. So a rectangular laminate plate is to be designed for carrying NX 100 kilonewtons meters, NY alpha times, NXY beta times, where alpha and beta can be between 0 and 1, but later on I'm going to actually specify alpha and beta to be actually 0.30 for case B, and 0 and 0.4 for case C. So there are 3 cases that this plate should be designed. So three little design problems. Once you solve once, then you should implement the same procedure for case B and case C. The laminates to be made only with 0 and 9 degree orientations, using the following stacking sequence. It's a symmetric laminate, but the number of 0 degree layers is n, which is an unknown, and plus minus 60 orientation angles is m, which is also an unknown. So basically your design problem is to find m and n, and whether you do this as a integer number. I guess integer number is preferred. If you know another way to do it, you can do it, but I will basically let you try m and n as integer numbers. And the requirement there is for part A or part 1, we're going to find m and n for these 3 different load conditions, so that the laminate will not fail based on Psi-Hill failure criteria. Okay, this is just a strength design. Once we have a good handle on this, then we will have part 2, where in addition to the Psi-Hill failure criteria, we're going to also have a requirement that E sub phi is some direction in any direction around 360 degrees. That the minimum in-plane shear stiffness should be more than. Actually, this should be greater than or equal to. I don't know if I can make this equal. There must be a sign for this operator. Here they are. Okay. Question mark. This I'd like to get a good handle on part 1 before I specify this. This will be normalized with the shear modulus of a single layer. And when we put up a layup like this, you're actually likely to get larger than 1 shear stiffness for some laminates. But I don't know if question mark will be 1 times G12, or I can actually also put here's question mark times G. Where G12 is the 5.59 gigapascals. So this would be, I don't know whether it's going to be 1 or 1.5. I'm going to decide on this E sub phi requirement once I see the kind of designs that we're getting in here. The material properties given are for boron epoxy with a layer thickness of 0.125 10 to the minus 3 meters. These are the moduli of the individual layers. And these are the strength properties of the material, all in megapascals and gigapascals, and etc. So this is pretty much it. Now, is this somewhat of an open question? That is it possible that different people will come up with different designs and will be able to defend them? Yes. is there a design which is the best? I suppose yes, but that will mean using some optimization techniques. And that's something that we haven't done yet. And after we do some bending response analysis, we're actually going to look at the final stages of this course using optimization techniques such as integer programming or genetic algorithms to design laminates using optimization techniques. But for the time being, for this homework problem, it is an open design exercise. I'm going to accept whatever you can come up with, provided that you use good engineering judgment. So what is a good engineering judgment? Can be a little thick, heavier, but not 10 times heavier than required. You know, as you increase M and N, definitely stresses are going to go down. So you're going to meet the Sahil failure criteria. Definitely, if you use way too thick of a laminate. So the problem actually, in fact, should be cast as minimize the total thickness of the laminate while satisfying the stress criteria as well as the stiffness criteria. So I was going to ask somebody who already had optimization if he wanted to do this as an optimization problem, but he's not attending today, so I'll leave that as a separate question for him. Anybody else who has optimization background and would like to use some optimization tool, I'm willing to work with him right now. But as I said, it's a topic that we'll cover later on anyways. Any questions? Claude just joined. So he did not hear any of the discussions, but we were talking about the test 1 assignment, part 1. And this is a version of this is on Blackboard, except I made just minor changes right now. Saying question mark will be defined later. And did I make any other edits? Probably not. Questions? Okay. In that case, we continue with the lecture, and then the next topic will be actually bending. So we're going to probably also look at some bending equations for laminates. And there's a yes, Claude says yes, I saw the tests as I was coming in. All right. I did some explanation on this. If you need, you can later on call me or text me or send me an email message with your questions. So I'm not going to repeat what I just said. The design problem is to find M and N so that this stress requirements are satisfied. All right, so I'm going to close this file, save, and go to my, I think what we were doing the lecture, and I stopped in the middle of the stiffness properties, because I thought that that's what was needed for test 1. And what we left out was the in-plane lamination parameters, or what is commonly referred to as Miki's diagram, using the name of Mitsunori Miki from Japan, who came up with this diagram some years ago. But let's go over the lecture that we did. We are basically limiting ourselves to in-plane stiffness matrix. B is absolutely 0, and we're not considering any bending action. So kappas are absolutely 0. So stresses in each layer is Q bars times the strain in the laminate, where these epsilon x, epsilon y, and gamma xy are actually constant through the thickness. In every layer, it's the same, based on the assumptions that we made for classical lamination theory. From that, using a stress strain analogy, sigma epsilon, we came up with some EX, EY, GXY, gamma XY equations in terms of the A matrix. And then we wrote the A matrix in terms of what we call these invariants, and came up with a matrix form, the A matrix properties, A11, A22, A12, A66, A16, A26, which are written in terms of V0 for A, and V1 for A, and so V0 times U1 will be A11 here. What is V0, V1, V2, V3? We said those are the integral of where are they? Yeah, those are the integral of some quantities that are cosines and sines of the 2 angle and 4 angles. V0 is constant, V0A is H, V0 of B is 0, V0 of D is H cubed over 12, okay? And V1 of A is truly thickness integral of cosine 2 theta dz, V2 sine 2 theta dz, etc. So that's how we are able to write these A matrix. From that, we could actually go to in-plane stiffness design. These are now the normalized version of the V's by dividing them with 1 over by H, the laminate thickness. So V1A was minus H over 2 cosine 2 theta dz. V1 star is of A is 1 over H minus H over 2 to H over 2. And so is V3 defined in this fashion. Now, our fiber orientations, although we are integrating cosine 2 theta, our fiber orientation is actually constant within each layer. So going from H over 2 minus H over 2 to H over 2, the fiber orientation is constant for one layer, thickness T, jumps to another value for the next layer, jumps to another value for the next layer. So it's actually piecewise constant theta. If this is the case, we can replace those integrals with summation and perform the integration for each layer. Since they're constant within that layer, they come out as constant cosine 2 theta k. So the integral becomes summation over the number of layers, k from 1 to n, and integral of z constant times cosine 2 theta will become cosine 2 theta will come out the integral as a constant. It will be integral dz, and that will be equal to z minus zk minus 1, which is nothing but the thickness of that particular layer. Zk minus 1 is just one layer thick. Now, if we do this integration for discrete angle of theta, where theta is plus minus theta I running from 1 to capital I. So let's say, just like your test problem, there are only 3 angles, 0 degree, plus degree, minus 60 degree. In this case, capital I is actually two distinct angles, 0 and at 60. And the sum of these different thicknesses will give you the amount of thickness of the particular orientation angle within the laminate. So V sub I is the total thickness of, say, 0 degree plies, V sub 1. V sub 2 will be the total thickness of plus minus 60 degree layers in the laminate. So same thing with V3, and then the total thickness, since this is divided by H, total V sub i's, this is like thickness ratio of one ply angle within 1 out of 1. So V sub I, summation of V sub I is equal to 1. Total thickness is equal to H. So sum of VI, sub VI, small VI's are equal to 1. If we do this, we find something very interesting. That when V1 is one angle, okay? No other angle, theta I is one angle, and it's plus minus theta. So capital I is not 2, but 1. When capital I is equal to 1, we have only plus minus theta angle. I equals 1 to 1, I is equal only 1. So V1 star is V1 cosine 2 theta 1. Or 2 theta, there's no need to call theta 1. So V1 comes out to be cosine 2 theta. If we look at V3, V3 comes out to be 2 times V1 star, which is this one, square minus 1. Okay? These are because of the trigonometric relationships. V3 was actually cosine 4 theta. So we are writing cosine 4 theta in terms of cosine 2 theta. If we do that, V3 will be 2 times cosine 2 theta square minus 1. Pure trigonometric relationship. What we have now is a parametric curve that when theta is equal to 0, we have a point which is here. When theta starts increasing, this equation gives you the coordinates for V1 and V3, or V1 star is actually decreasing towards, because cosine 0 is equal to 1, so V1 star at its largest value, 1. As your angle orientation increases, you're going to be marching along this line until you reach when V1 star is equal to 0, 45, you reach V3 star to minus 1. And then this is plus minus 45 degree. Then if you keep increasing the plus minus theta towards 90, you reach this point, where at this point, theta is equal to 90 degrees. when theta is equal to 90 degrees, V1 star is equal to -1, and V3 star is equal to 1. So this equation is basically, if I put this into a presentation mode, I can draw something to show what I'm talking about. Let's make it red. When I'm changing the ply orientation angle from 0 to 90, I am getting all these points continuously as I increase my theta. When I reach 45-degree ply orientation, plus minus 45, I reach this point. And then when I continue increasing plus minus theta, I actually, without wiggling, reach to this point where this is 9-degree plies, plus minus 90. And this is plus minus 0. And this point is plus minus 45. Basically, every one of these points is a laminate, regardless of the thickness of plies that are made of plus minus theta. No other point is possible with this condition that we only have one angle, theta. Okay? So in the previous equation, in the previous chart, there was an equation, there I is equal to 1. Only one orientation angle as a plus minus laminate. And these are the 3 points that I already marked on the chart, points of interest for us. Okay? There's another point marked in there, here. This is actually a quasi-isotropic laminate, and you can reach it with 0s, 45s, and 90s, but it's in the inside of this domain. It's more than one angle. So this gives a hint that some other combination of V1 star and V3 star, you can reach a V1 star of 0, a V3 star of 0, and that's going to be a quasi-isotropic laminate, regardless of the orientation angles, as long as V1 star is equal to 0 and V3 star is equal to 0. All right. So what do? We try two different angles. We make, say, I equals 2 or larger. But 2 is enough. Okay, so let's make it capital I to be, say, 2. So I have a theta 1 and theta 2. Okay? And I'm going to use these as, again, if you want, as plus minus, or I can also use them singly. In that case, in the previous chart for I equals 1, this was an equality. As soon as you go to I equals 2, you get an inequality. I'm not going to get into the mathematics of it or anything. In fact, the more general form of it has a lot more equations to consider. But for us, we're just looking at in-plane properties. So it will become an inequality. An inequality will immediately mean that besides the boundary here, any other point within this shaded region will satisfy this inequality, meaning that all the points inside are option for us. We can have in-plane stiffness matrix completely defined by V1 star and V3 star instead. These are star quantities. V1 star and V3 star. So in the previous chart. And we can write V1 star to be percentage of through the thickness percentage of theta 1 degree orientation angle times cosine 2 theta. It starts jumping on me again. And then percentage of the theta 2 orientation angle through the thickness, and V1 plus V2 is equal to 1. And then V3 star is V1 cosine 4 theta 1 plus V2 cosine 4 theta 2. Let's look at some laminates that we can have. If you put equal amounts of 0 and 90 degree plies, this means N, symmetric or unsymmetric, since we're looking at just in-plane properties, we don't really care that much, but ideally this is N symmetric, so that we don't worry about bending extension coupling and things like that. So if you take just 50% 0 degree plies, 50% 90 degree plies, what we get is V1 star to be 0, which is this value, and V3 star to be 1, which is going to be a point right here. Now remember, this was purely 0 degree ply. This was purely 90 degree ply. And this was purely plus minus 45 degree ply here. These 3 points, this point, and that point. When we have a laminate which is 50% 0, 50% 90, we get halfway between 0 and 90. Okay. Now, if your laminate somehow had 3 plies of 0, or 2 plies of 0 and 1 ply of, I'll make it 3 plies of 0 and 1 ply of 90, then the relationship is linear. You're going to get this point halfway in between 0 and 90. So this point can be, since these are normalized, the thickness is immaterial. Okay, thickness is completely out of the picture in this diagram. So this is actually 3 zeros and 190. If you have 3 90s, then you will have 0 and 90 sub 3 here for the laminate. If you take 0.2 plus minus 45, then you get V1 star to be 0.5 and V3 star be 0. So 0.5 will give you about here, V1 star 0.5, halfway here, and V3 star 0, so it will be a point somewhere here, okay, halfway between this and this, and somewhere in here. Now, what is that point? Actually, geometrically, if you look at it, it's the halfway between this straight line that connects 0 to plus minus 45. Okay? So this point here is 0.2 slash plus minus 45. Now, if you take, say, two 90-degree plies and plus minus 45, then you get a point about right here. And that will be the halfway between 90 and 0. Not curve, but straight line from plus minus 45 to 90. So this is a 90-degree twice slash plus minus 45. So you see what's happening. This point here, when V1 star is equal to 0, V3 star is equal to 0, is quasi-isotropic. Okay? Can you tell me a quasi-isotropic laminate based on this discussion that I can put in here? Or in this diagram here. And let's make it so that it is not the one that I'm showing here. That will be basically 0 plus minus 45 and 90. How is that found? How is that determined? If equals amount of 9 degrees and 0 degrees, always give me the point here. Equal amount of plus minus 90, oops, jumped again, and 45 is halfway between these two. Okay? So I get a quasi-isotropic laminate with joining equal amount of plus minus 0 and 90. This is 0, 90. And half 0, 90, half plus minus 45, I get quasi-isotropic. Can you tell me other quasi-isotropic laminates? Remember the 0 plus minus 60? Where do you think that is? No, don't jump. Okay, where do you think 0 plus minus 60 is? This point here is plus minus 60. Two-thirds 0. Don't jump. This is ridiculous. Why does it jump all by itself? I'm getting spooky. I'm not touching anything. It's just doing it. Okay, so 2/3, the distance from 0 to 90. This is 1/3. This is 2/3. Okay, 0 plus minus 60 is laminate which has that ratio. Or 90 and plus minus 30. Now, this basically tells us something else. There are potentially infinitely many laminates that are quasi-isotropic, as long as you can determine their proper ratio going from one end to another. So if I'm going from here to here, and if I know what this angle is, and if I know what this angle is, I can use equal amounts of those angles and find the quasi-tropic laminate here. I can go from here to here, and if I use this distance, if I have enough thickness in the laminate, I can come up with integer number of layers that give me this ratio. The angle here and the angle here will be sufficient to define a quasi-tropic laminate. So is any other point in this diagram. If I want a laminate with stiffness properties, that will the A matrix that gives me V1 star of some number and V3 star of some other number, I only need basically find the angle that corresponds to that point. That will give me the V1 star and V3 star. So I can actually start solving very neat problems. This was what we were doing with V1 and V2. So, for example, we have a relationship with two angles of this form, and we also have the requirement that V1 and V2 equals to 1. So if we specify that fraction, you don't jump, please don't jump. While I'm talking, the bar underneath keeps, to prevent the jumping, I can get out of the show. Okay, but I cannot write in that case. I can actually solve for theta 1 and theta 2, and I can come up with two equations for given V1 star and actually this is just in terms of V1 star and V3 star, and small V1 and small V2, I can find those angles to actually, let's see, to come up with the laminate orientation angle. So let's, I think I have an example for that I will do right here. So I'm going to try to find 16 ply laminates with lamination parameters given as V1 star equals 0.5172 and V3 star equals 0.3673. And this is actually completely defines the stiffness matrix. So the equation for T1 is either 0.9 or 0.13, and corresponding T2 for that is 0.38 and 0.64, and the angles come out to be 12.9 degrees and 33.5 degrees. That's a laminate that would give me the basically in-plane stiffness property that I desire. And then there's a second also laminate that satisfies the same stiffness matrix. So same in-plane stiffness matrix can be obtained by very large number of ply orientation angles, stacking sequences, as long as you're able to let the percentage vary continuously. If it's discrete, then the problem becomes a little more difficult, because in that case, this diagram, only certain discrete points are going to be feasible. And those actually will follow a neat pattern, but it's an integer programming problem that can be only solved using integer programming algorithms. So these are some of the laminates that you can find. I'm going to let you guys look at these examples. But basically, to build the Miki's diagram, you identify the selected single orientation limits on the diagram and the boundary of the diagram, and if they are inside, you can connect single orientation points to form a polygon, and for n plies, divide the polygon boundaries into n over 2 equal segments and draw lines from the boundaries. And if you, these are going to be all symmetric, but if there's a requirement on limits being balanced, then you have to get rid of some of the other points in there. This is already covered, but we have the engineering constants in terms of A's, but you can also find the engineering constants in terms of V1 star and V3 star, which means that the modulus E and G and nu are actually linear expressions in many cases in the lamination diagram, not EX. Nu and G are actually linear expressions. V3 star equals U1 star. So GXY is linear in V3. So those are basically horizontal lines in the diagram. The shear modulus values will be basically based on only horizontal lines going like this. And then Poisson's ratio will be straight lines in this diagram. And EX and GX will somewhat follow these boundaries, but they can be plotted. So there's actually a chapter in the book that I'm going to put about this topic that you can see. Somebody remind me via email to put that chapter about Miki's diagram on the blackboard. I may forget between now and the time that I turn off my computer today. So this is the in-plane stuff. Before going into design optimization, we're going to next start looking at bending. And to do that, we're going to do systematically, starting with from equations, and we're going to reduce to a simpler problem of what is called cylindrical bending. And then afterwards, we're going to go into something that we'll call beam column. So you can do composite beam designs and cylindrical bending of composite laminates in 2D. Any questions about this topic? No questions. All right. So I'm going to close this. Save. And go to my next lecture, which is in-plane plate equations. But I think I'm going to start doing that with the tutorial version of it, and then I'll show you the lecture version of it. All right, I don't think I need to initialize the CLT environment for this. We'll see. The figures in here is a bit misleading in terms of the exact notation, but it will give you an idea that stress distribution within the laminate in here is not continuous like this. It's actually piecewise linear, jumping from one layer to another. But if you consider these, say, to be NX, MY, NXY, and MX, MY, MXY, then these are copied from a isotropic plate expression chapter. So these figures are misleading. What's really important for you is we have these partial differential equations in terms of the stress resultants that we need to solve in order to actually solve a problem. In the case of in-plane, we basically said that there are no B matrices, no kappas, so we wrote the expressions between n and epsilon, which for the in-plane analysis, partial nx, partial x, plus partial nxy, partial y is equal to 0, and partial nxy, partial x, partial ny, partial y to be 0. If we actually go to this is not the correct. I did this for in-plane. Did I share this file with you guys? I should have done that. I did the constant stiffness limits, but that's the bending equation. Yeah. So this was the in-plane. If we go to the bending case and put the nx, ny, and nxy into the bending equation, then we have a third equation for the W. Now the first two equations, equation here, constant stiffness limit, I also put the derivatives pulling the constants out. So the D matrix comes into picture, which has the W, which is the out of plane displacement, as a third expression in there. However, there is a nonlinear term in this three equations, and that one is in here. What this is, an x, which really is not expanded like from here. Nx is equal to A11 epsilon x, A12 epsilon y, A16 gamma xy. We're going to still assume D matrix to be 0, but the D matrix is there for bending problem, and Nx will have D11 kappa x, and etc. in there. So this is a much more complicated problem that has to be solved in order to do the analysis of these plates. And even if you simplify to be mid-plane symmetric, eliminating the coupling, these are now expressions for nx, ny, and xy. And this becomes the bending stiffness matrix that has to be solved. And for balanced laminates, you can also get rid of 1/6 and 2/6 term in here. In that case, you have UV expression to be solved using this equation, and then you have to also solve this equation. And they're actually not completely uncoupled. Now, if you go to cylindrical bending, we can simplify these equations to a point that we'll be able to use reasonably comfortably using mathematica. Just like we assumed uniform stress state NX, NY, and XY everywhere for the in-plane problem. We're not going to get a constant stress distribution inside. We're going to get a variable stress distribution. But it's going to be a function of only one coordinate. So let's proceed with this. And what we do is we say any term that has variation, say, with respect to y, to be 0. Any term that varies with y, partial y, has to be 0, because we're going to take a laminate and we're going to bend it as a cylinder. Okay? So along the x direction, we're bending it. In the y direction, everything remains constant. Okay? That means variation in y direction is basically non-existent. Any partial derivative with respect to y goes to 0. If you do that, this expression reduces to this one. Note that we're still keeping a 1/6 and a 2/6 term. Second expression becomes this, and third expression becomes this. And for constant stiffness laminates, we can always take the A11 out and write it just like A11 times partial square U partial X square here. And then NX will be still simpler, but still more complicated than the simple. These are going to go to the bending equation. For balanced laminates, A16 and A26 are also 0, in which case it's even simpler for symmetric laminates, and the NX again is simpler. So balanced symmetric laminates, we get these with the third equation given in here, with NX given with this term only. You see, NX is actually a function of U0, and it comes into the bending equation here. So it's a product of in-plane displacement times the out-of-plane displacement, which is the nonlinear term. For constant stiffness laminates, the constants come out, and basically for balanced symmetric laminates, this will be the only expression that needs to be solved. That you can see that actually, if you have an x that somehow is constant, you can actually have a linear expression here. But for that, partial u, partial x must produce a constant term. So this is the cylindrical bending. It's a limited problem that we are basically taking a laminate, and we're going to be bending it into a cylindrical form like this. This is what we're going to be solving. And to bend it into cylindrical shape like this, we are putting an out-of-plane displacement force Q, which is shown in here, and bending it like that. So you can have a simply supported laminate here, bending like this, and we can also assume that this dimension is also there is no movement in there, so we can solve a plane strain problem like a beam. So we can actually start writing column beam equations for this kind of a thing. That by putting support in here and putting out of plane loads into the laminate, we're going to be able to design layups laminates in pure bending. I am going to actually show that with a tutorial how we solve these differential equations. They're coupled in next lecture. Once we are able to do that, we'll be able to compute stresses and displacements of a laminate under pure bending, so that we can start designing for bending loads. So that's sort of the lecture. I used the tutorial for this, but there's another tutorial on this to solve it. Actually, the lecture of this was also Mathematica notebook, but it is prepared as a presentation charts. So, as you may or may not know, there is format for style presentation. Do we see presentation? Where is presentation screen environment? Slideshow, yes. So there's a slide, a style sheet. Under style sheet, you can use presentation tools. There's article style, book style, report slideshow style, and under slide show you can have different options there. This is chosen garnet for some reason, and when you do that, you jump from one chart to another by using this. But in fact, this is presentation style, but still works just like Mathematica. But page length is limited, so I cannot go up and down in this. This is just one chart, single first chart. This is slide 0 of 4. And next chart, I can click in here. Takes me to the next chart. My equations are there. And I can actually type my equations using Mathematica in here. So these are basically the same equations that were in the notebook. But again, length of this is going to be limited. Next chart will be second chart of yeah, I deleted the other charts from this to simplify into another form, and I forgot to put the charts back. So slide 2 and 3 and 4 are empty right now. So only a chart slide 1 And yeah, only slide one exists. I'll put this, the other equations in there and post this as well for before the next lecture, so that we can actually solve the problem that we want to solve under cylindrical bending. That is about it for today. Do you guys have any questions about the test, about anything else? I forgot how to edit these things. Let's see. Yeah. I can probably copy and paste. Yep. This is the title. Okay. Questions? No questions? Cylindrical bending, beam. The only other thing that I can show you, let me do that. I forgot to edit the course document, and that probably is still 11th. Yes. And cylindrical bending. We'll just start with those equations next time and solve them to, that's the 18th next lecture. Okay, and then we're going to go for design for bending. Then we're going to solve it. Then we're going to go and start, I think, the design optimization. All right, so I'm going to save this as $216. And then go to contents, course contents, course documents, 216 files. Browse files. Syllabus 216. I'm done. You can drop out or you can ask questions. I will keep it on until after 5 minutes for. Thank you. Thank you, Mary. Thank you, Mohan.